It's about space technology. The Space Technology Mission Directorate pushes us to develop technologies that make NASA missions more affordable, more capable, and more reliable. This is a critical milestone for our composite cryo tank project with the arrival of the tank here at Marshall Space Flight Center. This is the culmination of about 2.5 years of work for the project. That included more than 3,000 coupon and subscale manufacturing demonstration tests, as well as a half-scale, 2.4 meter, 8-foot tank that we tested here last year.
This is a team that consisted of NASA and Boeing. We were under contract to Boeing to actually manufacture the tank, but it was a team effort. It was a really good team. We had really good work between the centers, and there was a lot of interaction between Boeing and NASA. It wasn't just a Boeing-built tank. It was a collaboration between all parties.
Well, another thing I particularly enjoyed about this program was the interaction with the NASA people. We had NASA people down for every critical phase of the manufacture, not only giving us advice and helping to mature the technology, but doing hands-on fabrication.
So to design and manufacture this tank, we use new materials. We process the tank by automated fiber placement. The benefit of that is we can lay down the material quickly, which provides us a low-cost operation and a very lightweight tank.
We've worked on this program for 29 months, and when we started, we'd never built a tank of this size by the methods that we did. We did automated fiber placement and fluted core, just developing the robotic fiber placement equipment and way to make the skirt in one piece was a large challenge.
The composite tank that we have here today is the largest ever of its kind. It's one of the largest composite tanks ever manufactured. The tank is larger than most launch vehicle tanks today.
We looked at testing the tank elsewhere in the country. We surveyed a lot of different places, and Marshall had the best mix of available capabilities to pull this job off. And so everywhere from moving around the center to processing it to applying the structural loads. There's just not a lot of places in the U.S. that can test something on this scale. The load is what's imparted to simulate launch conditions. So as you've got a rocket and it's going up, you get a compressive line load. And so that's what we're going to do with this ground test article, is apply a representative compressive force, which would be similar to what it would see during launch.
Our composite tank is designed to be 30% lighter than the state-of-the-art, and at the same time 25% less costly. We're performing this composite tank technology development for a number of stakeholders. First, to meet our NASA needs. We need to reduce the weight of our launch vehicles today, but there are many other stakeholders. The Department of Defense, for example, for their launch vehicles, and then other customers in the commercial arena as well.
The NASA Space Technology Mission Directorate is setting out to take on high-risk, high-payoff technologies, things that will be transformative in how vehicle programs will achieve their future missions. Being able to prove out that we can design, build, and contain liquid hydrogen with only using composites would be a significant breakthrough.
It's all about technology. If you don't develop technologies for the future, you won't go where you want to go. Composites will decrease the weight of the tanks. It'll increase the payload performance of the launch vehicle. It'll give us, it basically enables things that we don't have today.